Hello everyone, this is Adhish. I'm a grade 10 student from Mumbai. So today's problem is optimal sorting. The difficulty level of this problem is easy because it would come under 1500 to 1800 on code forces, and the only prerequisite required to solve this problem is a multiset, which is a balanced binary search tree, and multiset is the name given in C++ for this data structure. So in this problem, we are basically given an array of n integers numbered a1 through an, and we can perform the following operation any number of times. We choose any contiguous subsegment al through ar of the array, and we sort this element in non-descending order, or basically ascending order. If the elements are equal, then we call it non-descending order, and we need to keep all the other elements outside of the range L to R the same. So the cost required for this subsequence, to sort this subsequence in increasing order, would be the maximum of all the elements in AL through AR minus the minimum in this range. So for example, you can see that if you sort the elements 4, 1, 5, then the resulting sequence will be 1, 4, 5. And if you choose the whole segment 4151, then the resulting segment would be 1145, and the cost for either this or this would be equal to 5 minus 1, which is 4. And we need to determine the minimum total cost of operations. So we don't need to minimize the number of operations, but we want to minimize the total cost of the operations in order to make the array A sorted in increasing order. And let's take an example. So let's say we have an array 1, 3, 6, 7 which is already sorted. So in this case the answer would be 0 because we don't need to perform any operations. In the second example, we will need to swap 10 and 1. That's why we will need to perform at least one operation of cost 9. And since 10 is the largest and 1 is the smallest, we might as well sort the whole array in one go by a cost of 10 minus 1, which is 9. And for the third and final example, we could again choose the whole array itself, and the cost incurred would be 4 minus 1, which is 3. Another way to do this is described in the explanation, where we first sort the array from 1 to 4, and that results in a cost of 3 minus 1, which is 2. And then the resulting sequence would be 1, 3, 3, 3. Then we will then over here the array is already sorted, so we don't need to do anything. And then when we take the last element, so then when we take the last two elements, we can sort them with a cost of 1, and in this way the whole array is sorted. So 1 plus 2 is 3, and that would be the answer 3, which is the same as the answer you get for sorting the whole array. So the third and final example gives us a better intuition of how we might go about solving this problem. So let's analyze this example a bit more in detail. So let's say that the array was 3, 1, 3, 3, 4, 3 as in the third example. Then in this case we saw that we would first sort the portion from the range 1 to 2. So we would first sort this. That would be our first operation. Then we don't need to worry about the first two elements because they are already sorted in the correct order. We only need to worry about the remaining 4 elements. So we keep going one by one from left to right, and we keep looking at the elements. So far everything is sorted and everything is fine. We don't need to worry so far. And we get to 4. Then when we get to 3, so far we know that the segment from 1 to 5 is already been sorted, and we have reached the element 3. So in this case we know that we could just apply the operation on the range 5 to 6. So that would be the second operation which we perform on the range 5 to 6 to get the desired array. But how exactly did we know that performing the operation on the range 5 to 6 would give the correct output? What if the number was different? So what if in the example we didn't have a 3 in the end, but what if we had a 1 in the end? Then clearly this would not work. We would not be able to just swap the fifth and sixth element. So in this case we would again perform an operation on 1 to 2 for the first time. If we go by that logic, we would perform the operation on the range 1 to 2, then we would get this resulting sequence. And in this case, performing an operation on 5 to 6 would not give us the correct output, because if we perform the operation on the range 5 to 6, then the resulting array would be 1 3 3 3 1 4, and this is not what we want. So how do we figure out which operations to perform? So the key idea is that in order for the operation to be successful, we need to ensure that the first two elements are in the correct order in the sorted version. So in this case, in the left example, so if we compare the examples, in the left example, we know that 1 and 3 is the correct array in the original sorted version. So if we consider the sorted version, if we consider the desired quantity, we know that the desired quantity is these 6 elements, and in that 1 to 3, 1 comma 3 is the first two elements. However, 1 comma 3 are not the first two elements in the desired version of the sorted array, because 1 comma 1 are the desired elements, and by sorting 1 comma 2, if we by performing the operation on the range 1 comma 2, we are not achieving the desired objective, and that's why it's essentially useless to perform this operation, and we should not perform that operation. We should instead, in this case, we should instead go right till the end, because even if we perform an operation on the range 1 to 3, even then we would get something like 1 3 3, which is not what we want if we did 1 to 3, and if we did something else like 1 to 4, even then we would not get the sorted array which we wanted. We would get the sorted array only if we perform on the range 1 to 6, and that gives a cost of 3. So let's consider a third example in which we place a 1 somewhere else. So let's say that we placed a 1 over here in the third position. Then is it optimal to perform the operation on the range 1 to 3? It turns out that it is optimal. So it will be optimal to perform the operation on the range 1 to 3, because we know that in the resulting array 1 1 3 will be the sorted version. So we know that 1 1 3 is the same, basically the elements are the same in the original array and in the desired array, and that's why we perform the operation on the range 1 1 3. Then what do we do? So we figured out that based on these examples, we made the first observation that the first I elements which we sort, or the first operation which we perform, sorts the first I elements. So the first operation which we perform is like this, 1 to I, and we choose the I to be the smallest location, the smallest index, such that 113 is the same as 311, or basically in formal words, the first I elements in the original array A should be the same as those in the sorted array, and let's call that sorted array B. So we want to perform the first operation on the smallest position I, such that the multiset of the first I elements in A is the same as the multiset of the first I elements in the sorted array B. Now why would we want to choose the minimum value of I? Why should I be minimized? The reason is because, let's go back to the cost function. So the cost function is the maximum of all the elements minus the minimum of all the elements. Now the maximum value can only keep on increasing, and the minimum value can only keep on decreasing. And that's why the cost function will only keep on increasing, because if you increase the max value and if you decrease the min value, then this value will keep on increasing. That's why we want to make sure that in every operation we are reducing the number of elements in the range L to R. So that's the rationale behind why we choose the smallest index I. Now what do we need to do? What would be the second operation? That's the tricky part, and let's try to work through this example, figuring out what the second operation would be. So in this case, it's clear that we can just choose the range 4 to 6 and sort all the elements in the range 4 to 6 to get 3 3 4, and in this way we can perform only one more operation, or the cost would just be 1 and the total cost would be 2 plus 1, which is 3. and that would be the output. But how exactly did we choose the range 4 to 6? So the reason behind choosing the range 4 to 6 is that the first three elements are already sorted. So why should we worry about them? Why should we increase the size of the range if we know that the maximum element will only increase and the minimum element will only decrease if we extend the range? That's why we should always try to limit the range to the next set of elements, and we should always choose the elements in the range I plus 1 to some next element j. So the second operation will be the range I plus 1 to j, where again j satisfies the same condition that the first j elements in array A are the same as those in the sorted version of the array B. So this would be the second operation, and you can see that from the example itself, where we choose the range 4 to 6 because we know that if we sort the elements in the range 4 to 6, then these elements are the same as those in the sorted array, and that's exactly why we would like to find the minimum value of j again. We would again try to find the minimum value of j such that the first j elements are the same in the array A as in the sorted array B, and we would essentially keep repeating this process of going from a position j to j plus 1 up till k, where we are trying to find the minimum values of I, j, k and so on. These would be the operations which we perform. And another way to look at why this works is because let's say that I was equal to 1. Let's say I was equal to 1. So let's say the array was already sorted and I was equal to 1. Then similarly j would be equal to 2 and k would be equal to 3. And in this way we would essentially be performing a total cost of 0 because the array is already sorted, and that's a border case, or that's a border case which you can use to make sure that this idea works, and that choosing the minimum value of I will always minimize the cost, and hence choosing the minimum value of each index such that the first k or first j or first l or first any number of elements are the same in the array A and in the sorted version of the array, and hence we just need to find out an efficient way to check whether the first these many elements are the same in the original array and in the sorted array. So let's try to tackle that problem. So this is the problem which we have reduced the original problem to. We just need to check whether the multiset of the first I elements in the array A is the same as those of the first I elements in the sorted array B, and we know that if you are able to efficiently check this, then we can repeatedly increase the answer by the value of the largest element in the range of I in the range of the previous position to I. So the answer would increase by the maximum of the elements in the range previous position to I minus the minimum element in the range previous position to I, and then we would essentially set the previous position to be I plus 1 because that's what we are doing. We are then setting the starting element of the range to be I plus 1 and the current element to be j for the next iteration, for the next operation, and these would be the two lines of code which you would do. So the maximum element in the range previous to I is actually given by b of I. And why is that true? That's because we know that the array B is sorted, so we know that it's sorted in non-decreasing order, or basically in increasing order, and that's why each element is less than or equal to the next element, and that's why prev, which represents the minimum index, which represents the left endpoint in the current interval which we are going to sort, and I, which represents the last endpoint in the interval which we are going to sort, would be the minimum value and the maximum value respectively. So we will essentially increase the answer by b of I minus b of prev, and prev will be said to be equal to I plus 1. So this is what we would do repeatedly whenever we meet the condition that the first I elements in array A is the same as those in the sorted array B. So if that condition is met, then only we will perform these two operations. So let's try to check this condition efficiently. So there is one key trick which is being used in order to efficiently implement this. So the key trick is that we will use two multiset. The first multiset stores the elements which are in array A but which are not in array B, and the second multiset stores the elements which are in array B but which are not in array A. And in order to update these multisets, let's say we are at a position I and we have successfully stored the first I elements in multiset 1 and multiset 2. So in order to insert, or let's say we have stored the I minus 1 elements, and in order to insert the ith element, let's consider the ith element in array A and array B. So the ith element, we will first of all, let's say we call the first multiset AB and the second multiset BA, because AB essentially will store the set of elements present in A which are not present in B. In set notation, this is denoted by A minus B. So it's the set A minus the set B, and BA stores set B minus the set A. So we will first of all insert the element AI in AB and the element BI, B of I in BA. Now in order to ensure that we are removing the elements which are present in array B, so we need to ensure that we are accurately storing the first multiset. So in order to do that, we need to remove the elements in array A which are also present in array B. So we know that the first I minus 1 elements are stored accurately, we know this. So we know that only the ith element could have been a problem, and in order to check that problem, we will essentially check if BA contains or if BA.count AI is greater than or equal to 1. If the number of occurrences of AI in BA is greater than or equal to 1, then we know that we can successfully erase AI from BA and also from AB, because we know that AI is present in both BA and in AB. So we will erase AI from both of these elements, from both of these multisets. And similarly, if the second multiset stores some extra element, so let's say that the second multiset stores BI, and BI is present in AB also, in the array A also. So if AB.count BI is greater than or equal to 1, then we know that array A also contains BI, and that's a problem, because then we need to basically remove BI from both the multisets, and that's why we will essentially do that. We will erase BI from both the multisets, and this is essentially the whole logic behind the updation. Now what we need to ensure is that after we perform these updations, we can check the condition. So the condition which we need to check is that are the first I elements in array A and array B the same? So in order to do that, we know that the first multiset and the second multiset both should be empty. This is because the first multiset stores the elements in A which are not in B, and since we need both the multisets to be equal to each other, we know that the first multiset should be empty. There should be all the elements in array A should be present in array B, and similarly all the elements present in array B should be present in array A, and that's why both the multisets should be empty. So that's the condition which we will check. So if both the multisets are empty, then we know that we can essentially just perform the following operations, which is increasing the answer by b of I minus b of the previous index and setting the previous index to be I plus 1. The previous index basically refers to the starting point of the operation. So we would set previous index to be So in this case, previous index would be I plus 1, because we know that the next operation starts from I plus 1 to some index j, and that's why previous is I plus 1 and the current ending index would be I, and that's why we perform this kind of updation. And now I'll show you the code. So note that this code which I've just written over here, ab.erase AI and ba.erase AI, is not very accurate, and this is a possible error which you could have faced in the contest. The correct code would be, so the correct code for each test case, we will take in the value of n and we will take in the array A, and we will maintain the array B to be the sorted version of the array A, and we will maintain the two multisets A minus B and B minus A. And in the main part of the logic, which is storing the final answer in the last position, and the loop. So in the loop, it's important to realize that there are actually two errors which can happen. The first error, which is more obvious with practice, is that you need to erase only one occurrence from the multiset. You can't erase all the occurrences, and that's why you need to erase the pointer which points at one occurrence, and that's why you should erase from AB the pointer which points to the occurrence of BI. So AB.find BI will return you exactly one pointer, and you should erase only that pointer. If instead you did AB.erase BI, then this should erase all occurrences of BI from the multiset A, B, and that's why it's going to be wrong to erase all occurrences. You want to erase only one occurrence, and that's why you should perform this kind of operation where you erase the pointer which references to only one position where BI happens to occur within the multiset AB, and you should do the same for all erase operations. So in all the four places where you perform the erase operations, you should erase only the pointer. And another not so simple or which is a bit harder to detect error would be to not check whether AB contains AI and BA contains BI. So this is actually an important if condition. If you submit this code without this if condition, it will get a runtime error, because BA need not contain BI. Although we have inserted over here, there could be some problem which you get if you submit the code without mentioning this if condition. That's why you should always be safe and check this if condition. So if BA contains BI and AB contains BI, if both those conditions are met, then we know that both these multisets contain BI, and that's why they need to be erased from both these multisets. And similarly, if both the multisets contain AI, they need to be erased from both the multisets, and that's why we'll perform the erase operations. So in this way, we know that the newly added elements are not only added but also removed in case they caused a problem, and in case they were present in both the arrays A and B. So in case that happened, we perform the erase operations in this kind of safe manner. So you need to ensure that the erase operations are always safe whenever dealing with multisets. So that's the key learning from the multiset erase operations. And in returning to the main part of the logic, if both the multisets are empty, then we know that array A and array B are equal, because then we know that A minus B and B minus A are equal to 0, and they are the null set, and they would be the null set only when both the arrays are equal. So that's why if both the multisets are empty, then we know that we can increase the answer by B of I minus B of last position. And again, a third possible error would be to not use long but to use int. In this case, you need to use long because the values of the elements can be up to 10 power of 9, and that would be too big to not, like 10 power of 9 into 10 power of 5 would be 10 power of 14, which would not fit within an int, and that's why long is necessary. And in this way, you can accurately represent the intervals in which you perform the operations. So these are the intervals 1 to I plus 1 to j plus 1 to k, and so on, and that's represented by the previous position and the current position I. So in this way we accurately maintain the intervals and find the total cost, and you can verify that this code does get accepted. So I hope you like this problem and my solution. If you had any doubts, do leave them in the comments down below.